My name is Avi Hardenstein. I'm the antenna designer at Xerox, almost from the beginning, so almost 10 years. So I've done all the antenna designs throughout the different generations. The challenge when you do antenna design in the case of a multi-radio, multi-antenna situation is always find the right balance between antenna gain, antenna efficiency, good coverage, and at the same time good isolation. And it's a lot of balls to juggle at the same time.
Hey, Avi, why don't you share a little bit of your background for everyone? Why don't you share a little bit of your background?
Background-wise, I've been doing antenna design for close to 30 years and doing RF design for over 30 years, doing military, space antennas, a lot of commercial antennas, Bluetooth, Wi-Fi, and been doing, more or less all the wireless communication probably since the middle 80s. So it's been a long time, and I've seen all the different evolutions. As Dirk mentioned, in the case of the XR family of products, the decision was to make the solution modular, so the antenna and the radio are sharing the same card, and so can easily be architectured to different combinations for 8, 12, 16 ports, or they can be grouped in a certain direction to give more coverage, better coverage in a specific direction. So this is the basic card, and you can see the 2x2 and the 3x3. I wish there was something to point at. But since we have either 2 antennas or 3 antennas, where the design starts is, first of all, oh, great, that would be good. Thanks very much.
Thank you.
So I just push. So first of all, this is the antenna compartment, where this is all the RF on either side of the PCB. So in a way, what you see here is a reflector that is divided into 3 sections. If this is antenna 1, antenna 2, antenna 3, you can see here is a corner reflector structure here, a corner reflector structure here, and a flat reflector for the middle antenna. So each one of the antennas is a dual band antenna, whether a 2x2 or 3x3. And the idea was that the corner reflector structure to enhance the directivity of the antenna. So what you get, sorry, this is my sketches and sketches, but in principle, this antenna is responsible for pushing a little bit more energy in that direction, in line with the antenna, and in line with the effect of the corner reflector. And this antenna is more kind of center beam, and this antenna is more pushing energy to the right. Ideally, if the isolation between the antenna was really good, they wouldn't see each other. But in reality, the isolation from antenna to antenna is like about 13 to 15 dB. So they do see each other, and when we do the radiation patterns on the antenna, we can see the effect of the nearby antennas. This beam does see some effect from these two, and we get some array effect. But in the overall, the idea, of course, is to have 3 beams pointed a little bit in different directions.
Version of Java.
Java, it's back to destroy us.
The idea is still to get the antennas looking at a little bit different directions from each other, so to get the overall more consistency, more stability, performance. And these antennas are dual band, not easy to do with a corner reflector structure. Corner reflector structures are usually narrow band, like 10%. In this case, it was quite challenging to get a dual band performance out of it. The basic element can be seen here. This is the radiating side, and this is the feed side. You can just imagine it's a two-sided PCB. And that portion in the middle is what we call a Vivaldi notch antenna, or you might compare it to a broadband dipole antenna. And so this area, that section over here, operates from about 3 to 7 gigahertz. And in order to get the 2.4 gigahertz, you can see this spiral section. So that combination of the overall length up to here generate a narrow band response just at 2.4 gigahertz. So the overall effect of that antenna is a balanced structure like a dipole. So the energy comes straight out of that antenna. And that antenna is adjusted such that the phase center of the antenna is more or less at the phase center of the corner reflector. So achieving better performance at 5 gigahertz, it's more designed for the 5 gigahertz, and kind of forcing the 2.4 in, where as we're going to talk about the 11AC solution, this is where I took care of the 2.4 a little bit better. And this is the overall, the 11AC solution. Very similar, the same two antennas are here, except for the middle antenna, which what I was trying to achieve with that in this solution was to improve mainly the 2.4 gigahertz compared to the 11N solution that I showed before, mainly improving directivity. By improving directivity, improving coverage at 2.4 and at 5 as well. What I'm showing here is I'm creating, in addition to the corners and the flat reflector for the middle element, right in this area, I'm adding a director. So I'm creating, I'm not going to call it a Yagi antenna, I'm creating what's called a Yagi effect. So like the popular Yagi antenna, so there is always for Yagi antennas, there is always a reflector, there is the driven element, and there is a director. And
maybe draw a Yagi on the board, kind of explain it.
Yeah, we can do it. So the old Yagis always started, the basic structure was always a reflector and a driven element. And then as people wanted more gain, they started to add directors to it. The more directors, the more directivity you achieve. Up to a certain point, it's a traveling wave structure. So at some point, it gets to a diminishing point that you don't get much out of it. So I'm doing the same thing, but in a way, that's the structure that is being formed, is being created. But for this antenna, you have the corner reflector, you have the driven element, and there is the director at that point that I'll show how it looks very quickly. And for the center antenna, it's got a reflector, driven element, and a director, and the left element is like the right element. Let me show you how it looks like. So this is the center element that carries the director that is being shared, as I mentioned before. That director is being shared by 3 antennas. So it's kind of we are getting a pattern on it. I hope so. Too late by now. But what you see again is the same antenna portion for the feed and the antenna element, but I'm showing here a director. Now it's again, Yagi antennas are narrow band antennas, maybe 10% bandwidth. So this director is really, you can see it's made out of 2 sections. One section with a small gap here and a longer section. So it's really optimizes both the 2.4 and the 5 gigahertz to be enhanced, to have their gain enhanced. And the nice thing, the beautiful thing, again, is that one director is being shared by both all three antennas. So it's very complex. Unfortunately, as you can see, the solution has to be compact, modular. I cannot use anything in between the module to enhance the isolation between the radios. I need to rely only on what's within the module itself. So in order to achieve isolation, so it's always, I have the reflector that needs to help me. And the challenge was, we know more or less what the isolation that we are looking for, which for the worst case, in the 16 port, when the modules are almost touching each other, they are within 1/10 of an inch, we need to achieve close to 40 dB isolation. So this is the basic, the starting point. If I cannot get close to about 37, 40 dB, I don't have a game. We're not going to achieve that simultaneous effect of two radios operating within the same enclosure. And actually, if let me go a little bit farther and show you some of the isolation. Actually, these are radiation patterns showing the 2.4 for the XR, for the 11N, and this is a 2.4, and in this case, you can see the pattern is a little bit pushed. On this case, a little bit the azimuth. The red is the elevation, and you can see it's pretty much. If this is the bore side, it's pretty much along the symmetrical along the bore side, where the azimuth is more either directed this way or for the other element. You can see the blue is more pushed, more energy is being pushed more towards the left, depending on the antenna element. That's in the case of a 2x2. As you go to the 5, you get a little bit more. You can see more effect. You can see that again, just pushing this direction. And then you can see in the azimuth for the other element, and more energy is pushed in that direction. This is, of course, this is just a slice, so you can imagine the beam is more like a three-dimensional. So definitely more energy is being pointed in one direction or another. And this is, of course, is in the far field. But when we talk about isolation within the box, we talk about near field effect rather than far field. This is, as Dirk mentioned, this is a new product, the 620 and the 630 that are coming to the market. Unlike the modular solution that we discussed up to here, this is a low-cost solution, and on one PCB, rather than trying to use the standard dipoles that are being, it's hard to get out of it much directivity. I decided in this case, since the array is mostly mounted on the ceiling, I decided not to try to use a dipole, but rather to use that ground plane, which is, even though you see circuitry, but in the middle layer there is all ground plane, and any of these antennas is what we call a bent monopole antenna structure, and the solution is Omni solution, but rather than trying each one of the antennas to make it Omni, I rather made them, each one of the antennas a little bit more directional. So if you look on that antenna and you have the monopoles spaced around evenly. Each one of those antennas is still omni, but with a little bit of directivity. And the idea is, since it's a 3x3 solution, it's an 11AC 3x3, so it's an interleaved solution. So this antenna connected to radio number 1, and depending if I'll have all six antennas shown here. So every other antenna goes to one radio, and the other antennas goes to the second radio. So by combining 3 antennas together, you get the benefit of getting the 360-degree coverage. At the same time, we need isolation between the antennas, or isolation between the different chains of the radios. So I'm achieving, in this kind of combination that you see here, the worst case at 5 gigahertz is about 37 dB isolation, which is right the borderline in order to get the 2 radios working without interfering with each other.
Sorry, so are these monopole elements are the separate elements required for MIMO from a single radio? Is that the case?
3 per radio.
Yeah, we have
chain.
we have 3 chains, so three antennas for 1 radio.
For each element for a 3x3 MIMO.
Right. 1 element per chain.
So if they're slightly directional, does that mean that with the multipath you're trying to capture, could that, I'm just trying to picture it in my head, but with it being more directional that you might not...
a little bit more directional. It's not, they're in the 1 to 2 dB gain, they're not 5-6 dB.
Right.
So they're still omni enough.
Right, so if you take it to where I was kind of going, if it was very high gain, you're suddenly getting too much direction that multipath isn't going to hit it's not going to hit, each of those.
Right. Well, again, because they are monopoles, and because the directivity is low, you still get, when you combine the 3 antennas together, and you still get both the omni coverage, and you still get enough overlap between the 3 antennas or the 3 chains.
Right. So the goal is obviously not to negatively affect the MIMO, but to still get a bit of it.
Right. And and this is as Derek mentioned, we are in the beta phase right now, so we are just getting to test it in all the different scenarios and to see how well it works, how robust it is.
And to date, it's working very well. Get high data rates at good distance.
Okay.
So you said you have 3, and then you have another interleave 3, and they're both on 2 different radios.
Correct.
You're getting 37 dB between every pair.
That's between 2 adjacent.
Every adjacent ones, yeah.
2 adjacent. Yes. So yeah.
That's a lot, but all I see is air.
I know. I mean, you can come to my lab. I'll show you. I mean, I have nothing to hide. Believe me.
We have some test results actually.
Trust me.
Yeah.
If I couldn't deliver that, I wouldn't be there. I mean, this is that simple. Either you can make it or you cannot.
Avi labors endlessly in his cave with his little X-Acto knife and copper tape.
Well, what do you think? All these
I can't tell you how many different versions of this he went through before he found one that met the specs that we laid down for him.
You're saying it's all in the antenna design, not in the...
Yeah.
Well, there's nothing
Well,
high attenuation.
Well, unfortunately, every time we go to a new generation, marketing and the mechanical engineer want to make everything smaller and smaller and smaller, and I'm pushing the other way in order to be able to achieve the isolation. So it's the challenge is always.
So when we were going from our first generation to second generation to the XR platform, and we were looking at how to do the shrink, Avi said, "Fine, you guys can make it smaller diameter. Can I have a foot in height?"
Yeah, unfortunately.
We said no.
Unfortunately, both the height of the reflector is critical in order to get aperture, to get gain, directivity. So as we reduce, we lose some of the directivity, unfortunately. So I was using before tricks as I was tilting the beam down, doing all other tricks. In this case, the energy just comes straight. Here, the energy, since it's mainly going to be used in that form, so the antennas are mounted from here. The energy is more or less is pointed a little bit down, optimized a little bit down, because it's a monopole on a ground plane, so you do get some beam tilt. Depending on the size of the ground plane, you get some beam tilt down, and it helps a little bit with coverage. Actually, the antenna element, you can see it from close up, looks like that. This is the feed point, and again, this portion works from 3 to 8 gigahertz, 3 to 7 gigahertz, and that addition here is the 2.4, and because it's such a narrow line, it's a very narrow band effect, but it's there.